Hey guys, welcome back to quantum mechanics. So today we want to pick up where we left off last time, which was in the middle of our discussion of our partial wave analysis for scattering. And we had peeled back several layers of the kind of proverbial onion, and we had broken down the scattering amplitude in terms of sub-amplitudes. And then from there, we were able to further break it down into uh, pieces that depend on this so-called phase shift. And we saw at the end of last time that we know that the cross-section, differential cross-section is equal to the amplitude squared of our scattering amplitude. And so we ended last time with a computation of the total cross-section, which is this thing modulus squared, and then integrating over the angular variables. And we found that the total cross-section takes a very simple form in terms of this expansion in the L squared quantum numbers, right? And so what we want to do today is try to figure out how do we determine what this phase shift is. And just remember that, this is an infinite sum. We're summing over all possible values of L here. But as we'll see, as I'll prove to you today, I think I've said it a few times, but as I'll show you today, and in low energy experiments where K here is small, you only have to consider the first one or two, maybe just the third, up to three of the terms in this sum. So it's manageable. Okay. All right. So how are we going to determine this phase shift delta L? Well, there's a good approach, and let me outline it here, and then we'll put it to use. Okay. So the first thing we're going to do is like what we always do, which is solve Schrodinger's equation. Okay. So we're going to have something like a case like this, and this is cartoon of our situation. This was just meant for me as a reminder, as I'm usually giving this lecture at the chalkboard. But so we're going to have some situation that looks like this. So we're going to have some potential. It's going to have spherical symmetry. It's going to have some boundary. It's going to have it's going to have some range. Is the word I was looking for. And so inside this range, I'm going to call that area the inside region, and outside of that range, I'm going to call it the outside region. Okay. And so what we're going to do is we're going to solve Schrodinger's equation both inside and out, and then use boundary conditions to determine any normalization constants, right? Just the normal prescription. And what we'll do then is we'll use the fact that we're dealing with scattered waves, and if there are any leftover constants or anything that we need to determine, we can always use the fact that we know the asymptotic form of the scattered wave function out as we take r goes to infinity. And from all of that stuff, we should be able to hopefully extract an expression for this phase shift. Okay. All right. So let's start with the outside region. Okay. So the outside region, we're dealing with spherical symmetry. There's no potential out there. It's a free particle. So we know what the solutions are, right? They're spherical Bessel and Neumann functions. Now, by definition, the outside region doesn't include the origin, right? So that means that we're going to have to keep the Neumann function. Remember, usually if you're solving inside or if you're solving a region where the origin is included, you usually have to set the coefficient of the Neumann function to 0 because it blows up at the origin, right? But here we're excluding the origin, so we have to keep both terms. And we know that we're interested in the large R limit when we talk about scattering experiments. And we've seen several times now how these guys kind of asymptote to functions that look like sine kr over kr, or cosine kr over kr, right? And so it turns out that these aren't necessarily the most useful form of the wave function in the outside region. That you can actually define new functions that are linear combinations of these guys, and things become a little more clear. Because remember, so we're interested in extracting outgoing and incoming waves, right? And these guys are going to be linear combinations, right? If I take sine and I rewrite it using my Euler identity, it's going to be a, e to the ikr, plus or minus e to the minus ikr, and so on and so forth, right? So what we want is we want to define some functions that asymptote to either outgoing waves, purely outgoing waves, or purely incoming waves, right? And those guys are called Hankel functions. I don't think I wrote the name down, but it's Hankel. But they're just basically linear combinations. So there's the first Hankel function. That's what this one here denotes. Is JL plus I in L, right? So, and as R goes to infinity, you can just plug in the asymptotic expressions for these guys, and you can do a little bit of algebra, and you can show that this first guy goes like basically an outgoing wave, right? It goes like e to the I kr over kr. So this is an outgoing spherical wave. And likewise, you can look at the second Hankel function, which is JL minus I and L, and look at the limit as R goes to infinity. And sure enough, you could show that the second Hankel function goes like an incoming wave, right? So this is what these are the two. We're going to replace spherical Bessel and spherical Neumann functions with these spherical Hankel functions. Okay. Don't get too caught up in this because it's just details, and it makes the asymptotic solutions simpler to extract and to evaluate. Okay, so what we're looking at is an outgoing wave function. Right, we're going to write it in terms of Legendre polynomials, and so this stuff I to the L, 2L plus 1. This is all just factors that usually come along with when you separate functions into radial and into angular coordinates. And we're going to have some coefficient A of L, and it's just going to depend on R, and that's going to be our linear combination of the Hankel functions, right? And so we're going to have these, in general, we'll have these coefficients, and these are the guys that we want to evaluate using the boundary conditions, okay? Okay, so, and it should be noted that these guys are going to be the ones that contain the information on the scatterer, the scattering potential, right? Okay. All right, so remember our goal is to try to extract an expression for the phase shift, okay? And what we're going to do is we're going to try to write these coefficients in terms of that phase shift, right? And to do that, we can try to make a connection with the expression of the total wave function, which include the incoming and the scattered wave function, and try to make a connection between these coefficients, CL, and the stuff we had before. Okay, so in other words, so this is an expression that we derived last time, I think, right? So this is a combination of the incoming wave and the scattered wave, right? And remember, we combined the two and wrote it in terms of an outgoing wave and an incoming wave, and they had coefficients. And I'm just now noticing that this is missing the A sub L, the partial wave or partial amplitude. But this is the coefficient, right, of the scattered wave. And remember, we said that if you turn the potential off, this term goes to zero, and so you just end up with back with the plane wave, right? And so what we did was we simplified the notation. We wrote this as S sub L, right? And then we used the conservation probability to say that up to some phase, the coefficient of this guy has to be equal to the coefficient of that guy, modulus, right? And so what we did was we took that information and we said, okay, let's rewrite this coefficient in terms of pure phase, and we put in a factor of 2 by hand. Okay, so in the end, our general scattered wave, which includes also the incoming wave, has this form, right? So the outgoing wave has this e to the 2I delta L, right? And so what we can do now is take the expression for the wave function that we just derived by solving Schrodinger's equation outside the potential and compare it to our scattered wave, and that way we can extract these coefficients, these C sub L's, right? And so if I compare the two expressions, right, and I take the limit as r goes out to infinity, I find that these coefficients take a very simple form, right? And this is the whole reason that we made that switch from the JL or from the Bessel and Neumann functions to the Hankel functions, because it makes this part of the analysis a lot easier. Right, so we just basically compare this wave function to the asymptotic form of this wave function, and we see that the coefficients CL1 and CL2 are just these simple things. So CL2 is just a constant, right? And CL1 is the one that carries all the information about the scattering because it has the phase shift, dependence on the phase shift. Okay, so we've got these coefficients in hand, so we can actually go back to the Bessel and Neumann functions, right? So let me do that. I'm going to rewrite this, the radial part of the wave function, plugging in the coefficients, right? So here's CL1, CL2, and rewrite these guys in terms of the spherical Bessel and Neumann functions. So I plug those back in, and now when I when I multiply these out and combine them and combine like terms so that I have the spherical Bessel function and the spherical Neumann function, and you look at these and you say, this is a cosine, right? And this is a sine. Right? So in the end, we can write this radial piece of the wave function as e to the I delta L, and then times this combination of different terms, right? Okay, so we've got our radial part of the wave function, and we're set to match on to the wave function from inside the potential. Okay, so this is where it gets a little complicated, and you'll see why in just a little bit. But what we're going to do is, instead of solving, because what we want is what we want is we want to keep the generality of the problem, right? So we don't want to say, okay, so here we're going to deal with a specific potential. It might be like the hydrogen, like a Coulomb potential or something like that. We're gonna try to solve this problem in general. Okay, so what we're gonna have is Schrodinger's equation with just an explicit dependence on V of R, where V of R is generic. Okay, hopefully it'll become more clear as I go along. But what we're going to do is, instead of matching, so typically what you would do is you would match the wave functions, right, at the boundary. Right, this is just like one-dimensional scattering, like where you had a potential that's larger than your incoming energy, but the particle can still tunnel. You remember, hopefully you remember this from your undergrad, and there's different things you can match, like the wave functions or the derivatives or whatever. Here we're going to do something slightly more complicated. We're going to match what are called the logarithmic derivatives. Okay, and you'll see why in just a minute. With a logarithmic derivative or bi-log derivative, I mean the derivative of the log of the radial wave function with respect to log of r, right? And why do I want to do that? Because if I take these differentials in, I end up with the derivative of our radial piece with respect to r, and I have this kind of factor out in front, which is r over a sub l, our radial wave function. And when we evaluate this thing at the boundary, we give it a special name. We call it beta. Okay, so the beta sub l is that thing, the derivative of our radial wave function with respect to r times r over a sub l evaluated at the boundary, right, of or the range of our potential. Okay, so let's see what it is for our, let's plug in our expression for this radial wave function and see how far we can take it. Okay, so we plug in that thing that we had, so that e to the I delta L, and then the combinations of cosine and Bessel and sine of Neumann, and we take derivatives with respect to r. The only thing that depends on r are the Bessel and Neumann functions, and so I'm just going to leave these as derivatives. So the prime here denotes a derivative with respect to r, right? And so I take this derivative, right, and then I have this factor of a sub l down here, and so I'm going to write it in terms of its expression in terms of cosines and sines. Okay, so on top we have the derivative term, and then down here we have a sub l. Okay, with some common factor k times big R, where big R is the range of our potential. Okay, so the idea is that we have this function, this thing, beta sub l, right? And the idea is that if we could somehow measure this quantity, beta sub l, we could invert this equation and solve for the phase shift, delta L. Okay, so this is some quantity that hopefully we can extract by doing our matching. And by doing that matching, we can invert this equation and solve for delta L. So let me show you how that's done. So it's just a bunch of algebra here for the next few steps. So I'm going to multiply both sides by this denominator, right, and then do some algebraic magic. And what I find in the end is that I can come up with an expression that looks like this. So the tangent of delta L is this stuff, okay? And remember, these are these Bessel and Neumann functions. We know what they are. They go like sines and cosines, right? And so for a given L, we should be able to come up with a number here, right? Because we'll know the initial energy, which is K, we'll know the value of the range, and hopefully we'll be able to measure what this beta sub L is. Okay, so the idea is that if we can do that, if we can measure beta sub L, we can derive a number for this phase shift, and then once we have the phase shift, we can go back to our kind of standard formula and be able to write down an expression for the cross section. Okay, so the big question is, how do we determine beta sub L? Right? And like I said, what we need to do is solve the Schrodinger equation inside the potential, and then match onto the solution from outside, right? And in general, or in simple cases, you can. So if it was like the Coulomb potential, you could solve, Schrodinger's equation inside. It would just be like the hydrogen atom. Or you could do something crazy like a simple harmonic oscillator potential, or something like that. But so you could plug in a specific V, one of these simple ones that you know how to solve, like the Coulomb potential or something else, and then match the wave functions, right? But in general, or in the real world, really, we don't have that luxury, right? The potentials are usually a little more complicated than just simple, Coulomb potentials. They might be screened potentials, or they might have just a completely different form, right? Depending on the fundamental force, right? So what we want to do is we want to try to solve this problem in general, okay? And so the way we do that is I'm going to write down Schrodinger's equation, right? But I'm going to use so this is just the radial part of the equation. And I'm going to use the form where we write it in terms of this U sub L wave function. And if you remember from last semester, we derived a bunch of different forms of the Schrodinger equation. And when we were talking about angular momentum, and we said that, depending on the situation, you can pick one of they're all equivalent, but one equation might be easier to work with than the others. Okay, so this is the equation I'm going to work with, right? And we want to solve this thing for some general potential, right? But like I said, most times it's going to be complicated, and really what you're going to do is you're going to in the real world, you're going to not be able to solve this thing analytically. You're going to have to solve it using a computer, using numerical techniques, right? And that is why we work with the matching the log derivatives instead of the wave function, right? Because what I want to do is solve for the derivative here, right? This is the second derivative. But what I can do is I can take everything over to one side and then do one integration, right? Do one integration over r, or one integration over this wave function, right? And when I do that, so if I separate and integrate, right, I'm going to have some dul over ul, right? So that's going to give me a log, right? Um, and I'm going to have one derivative left over, right? So convince yourself of this. So take this stuff over to the other side, divide through by L, multiply by one factor of dr, right? And then integrate. So you would have some integral of this thing. It's going to be a mess. That's why you want to do it numerically, depending on what this v is. But on the left-hand side, you're going to have one derivative left, and you'll have this factor r over a sub L once you plug back in what u of L is, okay? And that thing is precisely what we call beta, okay? So this is inside the potential, right? So we have this thing evaluated at the range or at the boundary of the potential. This is the beta sub L inside the potential, right? And so now, instead of matching the wave functions from inside and outside, we're going to match these quantities beta sub L from inside and outside, right? And in that way, we can, because remember, this guy in the outside is the thing that depends on delta L, right? So if we can derive some number for this, then we can use the expression that we had for this guy and just, for a given value of L, we can solve for the phase shift. Okay, so that's the general idea, right? In a real world situation, you don't always get to solve the Schrodinger equation exactly. A lot of times you have to do things approximately or numerically, right? It's just the way it is. Okay, all right. So let's consider an example, and I'm going to pick this easiest example there is. And it's called case of hard sphere scattering, okay? Or sometimes you'll hear it called the impenetrable sphere potential or problem or something like that. So basically what happens is we have particles coming in, right, in our beam. This is the range of our potential. And the potential is so strong that the particles cannot penetrate this region, right? So basically, we're taking the potential to infinity. All right, but outside the potential is zero. Okay, so there's free particle out here, and we have an impenetrable sphere. Okay, so outside the wave function, we can just write down what we had before. We know what the solution for the radial part is, right? And because this is impenetrable, because the potential goes to infinity, that means the wave function has to vanish inside of this region, right? So this is a very simple case compared to the more general case that I was talking about in the case that you might encounter in homework problems. But this is a simple case, right? And so what we can do is we don't have to basically resort to matching the beta sub L's because we know the wave function vanishes, right? So we can just use the fact that this guy evaluated at big R has to vanish, right? So this is what I'm doing here, right? So this thing has to vanish, And if that's the case, then I can solve for, and I can get a simple expression for my phase shift, right? The tangent of the phase shift in terms of these guys, and these are just numbers, right? So for any L, we can determine the phase shift. Okay, so for example, let's consider the simplest case where we have what's called S wave scattering. So this is where L equals 0. So this goes back to the old spectroscopic notation, the SPDF, I think, right? And so typically in scattering, we'll have usually only L equals 0 and L equals 1 terms. So we'll either have S wave scattering or we'll have P wave scattering, right? Or some linear combination of the two. So in this case where we just have S wave scattering, so L is equal to 0, we have tangent delta 0, and we just plug in zeros here, and we know what these guys are, right? They're just sine over kr and cosine over kr. And we can, so the kr's cancel. This thing gives me minus tangent kr. Use the fact that tangent's odd. And lo and behold, I can get a nice expression for my phase shift in terms of basically the initial energy, K, and the range of my potential, okay? And so you can go back now and plug in for delta 0, what you have, what you found, into your wave function, right? And you massage it a little bit, and you can get it down to this form where it's just a sine function. And so basically what the phase shift is doing is it's pushing the wave function out away from the origin, right? Which is what we would expect for an impenetrable sphere. We wouldn't expect the wave function to be able to go all the way to the origin. Okay, so finally, I want to show you that in the low energy limit, we only have to consider the first couple values of L. All right, so in this case, we're in the low energy, right? So we always want to deal with dimensionless quantities. So let me take K times R. So R is my range, right? But what we're looking at is cases where K is so small that this combination is much smaller than 1, right? So in this limit, we can, so what am I doing here? We want to rewrite the spherical Bessel and spherical Neumann functions in terms of the KR, the small KR limit, right? And in that case, you can write them in this kind of funky way, right? So it's KR to the L, and then 2L plus 1 double factorial, okay? And then something similar for the Neumann function. And if you've never seen the double factorial, that's okay. It's not used very much, but it's just basically like the factorial, but you skip, instead of subtracting 1 for each factor, you subtract 2, okay, all the way down to 1. Okay, but the important point is that, so let me take, okay, so now I see, so these should be capital R's, right? So I'm going to take the limit where K times big R is small, so that's why I've written it like that. All right, so I have my expression of tangent delta L in terms of the Bessel and Neumann functions. Plug in my small KR limit expressions. I can cancel some stuff off, or no, see, I'm just combining stuff. I don't think this should be squared here. I think it should be, I think that's a typo. But what this is, I mean, what you can see is that, so this is a general expression for our phase shift. And what you see is in the limit where KR is small, what's going to happen? So the denominator, as L gets big, is going to get big, and so it means it's going to, the number is going to get smaller in general, right? But if KR is less than 1, right, as L goes to larger values, this thing's going to get squared, then, to the 4th, to the 6th, so on and so on, right? And a small number raised to higher powers is going to get smaller and smaller and smaller. Okay, so this is showing you that really, in the low energy limit, you only really need to keep the first or second terms, right? So L equals 0, maybe L equals 1, right? Depending on how small the combination of KR is. Okay, so that's where, this is for the specific case of this hard sphere scattering, but same thing happens in general. Okay, so we have, so finally we can take our expression for our phase shift and just look at the S-wave scattering and compute the cross-section, right? So the cross-section, differential cross-section is our F of theta squared. In general, it's this, right? With L equals 0. And now I can plug in for the S-wave scattering here, delta. And there we found that delta was minus KR, right? But it's sine squared, so the sine goes away, right, over k squared. And in the limit where this guy is small, I can expand this sine squared, and it's going to go like k squared r squared, right? And so the k squareds are going to cancel, and so in the low energy limit, the differential cross-section just goes like r squared. And that's why we call it a cross-section, because it has units of area, right? And then finally, I can just integrate this thing over d omega, and that's just going to give me a factor of 4 pi, right? And so the total cross-section for this impenetrable sphere is 4 pi big R squared, right? And if you think about this, it should seem a little odd, right? Because if you go back to the picture of what we had, find it here, right? So this guy has a cross-sectional area, right? If you think of it in terms of you're riding in on this beam, and what you would see is a circle, right? And that cross-sectional area, the area of that circle is pi r squared, right? So you would expect that in the low energy limit, that this thing would or should reduce, or you would expect the cross section to still take that classical form, right? And what we see instead is that it's 4 times larger. Okay, and so what we'll do, we'll get into this maybe next time. I can't remember what we're doing next time, but at some point I'll explain this factor of 4, right? And it's a purely quantum mechanical effect. Okay. All right. Well, that's it. And I'll talk to you guys next time. Bye.